Day 647 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again. Another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 1382, balance a binary search tree. The difficulty level is medium, so you already know we're going to keep the solution as simple and easy to understand as well. But before we get started, y'all, don't forget to like, hype, subscribe, comment, and share. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. Given the root of a binary search tree, return a balanced binary search tree with the same node values. If there is more than one answer, return any of them. A binary search tree is balanced if the depth of the two subtrees of every node never differs by more than one. All right, y'all, so that sounds simple enough, but let's go ahead and take a look at these examples anyway, just to make sure that we are doing this problem correctly. So, in example 1, the input root equals the binary search tree 1 null, 2 null, 3 null, 4 null, null. Boom. Now, I just want y'all, before we go any further, I just want y'all to know how this reads. So, this right here is 1. This is the root. Then the left pointer is, or the left child is null, right? Because there is no left child of 1. And then we have 2. Then we come right here to 2. Boom. Then we come to 2. The left child of 2 is null. So then we come to 3. Boom. Now we're at 3, null. The left child is null. Then we come to 4, boom. Then 4, both children are null. So that's where this null comes from. Boom. Then our output is a binary search tree 2, 1, 3, null, 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 4. So that would be this one right here. So once again, 2 is the root, boom, or the head. Then 1 would be the left child of the 2, boom. 3 would be the right child of the 2, boom. Then 3 would be, then the left child of 1 would be null. That's where this null comes from. The right child of 1 would be null. That's where this null comes from. Then the left child of 3 would be null. That's where this null comes from. Boom. And then the right child of the right child of 3 would be 4. That's where this 4 comes from. So this binary search tree is this right here. But this is also a correct answer. It says this is not the only correct answer. The binary search tree 3, 1, 4, null, 2 is also correct. So as you can see, 3 is the head, boom. Then 1 is the left, boom. 4 is the right, boom. Then 1 has no left, so we could put the null. Then 2 is the right, so we could put the 2 right here. And then since 4 is at the end, we don't have to put those 2 nulls. So that's how that works. Now, let's get into the binary or the balance part, right? So it says a binary search tree is balanced if the depth of the 2 subtrees of every node never differs by 1. So as you can see right here, this subtree right here, this would be the depth right here. And then as you can see, there's only 1 extra node on this side, right? So the difference is only this 1 extra node. If this node had another child, right, on the left or the right, then it would not be balanced, because then the difference would be 2, right? Because there would be a node down here. But since this right here is, as you can see, this is the most, I guess, the bottom nodes, as you can see, they're all balanced, right? They all stop right here, except for this one, which it only has a difference of 1, right? It only extends 1 past the rest of the other nodes, right? So let's take a look at example, or this node right here, or this binary search tree right here. So once again, this is balanced because you see it only differs by 1. If this 2 had another node connected to it, then it would be balanced, then it would not be balanced because it would differ by 2, right? But since this only differs by 1, as you can see, the depth of the 2 subtrees, right? So this subtree and this subtree only differ by 1, just like the depth of these 2 subtrees only differ by 1. Same with this. The depth of this subtree and the depth of this subtree only differ by 1 with this node right here. So that's what makes them balanced. Once again, if this had another node over here, it would not be balanced anymore, because then it would be different. This subtree and this subtree would be different by 2. So Just in case that didn't make sense, y'all, let's take a look at example 2. In example 2, the input root equals a binary search tree 213. The output is 213. As you can see, the depth of this binary tree is the same. They both stop right here. So this this binary tree is already balanced. So since this binary tree is already balanced, we can just return it as is, y'all. So boom. Now, I hope that makes sense to y'all. And now that we understand the question, let's get into the fun part, the actual solution. Solution is not that difficult. Now, the first thing we're going to do is we're going to create an array to store the in-order traversal of the binary search tree. And the in-order traversal of a binary search tree is going to yield values in sorted order. So we could just come right here, declare a variable called traversal, set that equal to an array of integers, come outside it, put a parentheses. Boom. Now we're going to create our first depth first search to perform our in-order traversal. So we're going to say func DFS, open up the parentheses, we're going to say underscore node colon. It's going to be a tree node. That's going to be optional, so put the question mark. Boom. Open up the brackets. And we're going to create a base case to stop the recursion if the node is nil. So we're just going to say guard, let node, else, open up the brackets, and we can return. Boom. Then we're going to visit the left subtree. So we're going to say DFS, open up the parentheses, node.left. Boom. Then we're going to record the current node's value by saying traversal.append, open up the parentheses, node.val. Then we're going to visit the right subtree by saying DFS, open up the parentheses, node.right. Boom. Now we're going to perform our in-order traversal starting from the root. So we're just going to call DFS and pass it a root by saying DFS, open up the parentheses, pass in the root. Boom. Now we're going to recursively build a balanced binary search tree from the sorted traversal array. So we can come underneath this, create a variable called build, open up the parentheses, underscore L, colon, that's going to be an integer, comma, underscore R, colon, that's going to be an integer as well, and it's going to return tree node, put the question mark, and let's open up the brackets. Now, if the current range is invalid, then there is no node to create, so we'll say guard L is less than or equal to R, else we could just open up the brackets and return nil. Boom. Now we need to choose the middle index to maintain balance. So we'll come right here, we'll say let M equal, open up the parentheses, L plus R, come outside of that, and we will divide that by 2. Boom. Then we're going to create a node with the middle value. So we'll come underneath this, and we'll say let node equal tree node, open up the parentheses, traversal, square bracket, M. Boom. Then we're going to come underneath this, and we're going to recursively construct the left subtree by saying node.left equals build, open up the parentheses, L, comma, M, minus 1. Boom, just like that. Now we need to recursively construct the right subtree. So we'll come underneath this, we'll say node.right, set that equal to build, open up the parentheses, M plus 1, comma, R. Boom, then we're going to return the root of this balanced subtree by coming underneath this. We're going to say return node. Boom, and then we're going to build and return the balanced binary search tree using the full traversal range by coming underneath this function and saying return build, open up the parentheses, 0, comma, traversal dot count minus 1, y'all. Boom, that should be all that she wrote. Let's give it a run. Make sure it runs properly. Okay, we got our first error. Let's see. This is just spelled all wrong. Look at that, y'all. Let's go ahead and fix that and run that again. See if that did the trick. It's accepted, so let's go ahead and submit it. Make sure it's still accepted after we submit it. Let's see, and look at that, y'all. 10 milliseconds beats 100% of users. That's what I'm talking about. That's what I like to see, y'all. So before we go, make sure you get one more look at the code. This is the top part. This is the bottom part. And yeah, y'all, with that being said, I hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.